Everyone, got a second example here, and you notice there's two strain gauges. Two of them! Magic. So, what do we have here? Well, a 6mm thick rectangular alloy bar, okay, is subjected to a tensile load P by pins at A and B. Now, width of the bar W is equal to 30mm. Strain gauges are bonded to it and have the following strains in the longitudinal and transverse directions. So transverse going up and down, longitudinal going along the length. And those are 1,525 microstrains and negative 540 microstrains. And we want to know Poisson's ratio for this specimen. We also want to know if the measured strains were produced by an axial load of 27.5 kilonewtons, what the modulus of elasticity would be for this specimen. So, with that in mind, go forth and try this problem and tell me how it went. So I'll give you a few minutes to try, and then we'll come back and do it together. So 3, 2, 1, and we're back. So let's do it together now. Okay, Poisson's ratio isn't that hard because it gave us both of the strains. It gave us the transverse and the longitudinal. If you're like, but I needed the lateral, not the transverse, it's all the same, just different words. So negative the lateral over the longitudinal strain. Our lateral strain is negative, our longitudinal strain is positive, all works out. It comes out to be 0.354. It's very similar to what we had last time. Now the bar area is going to be 30mm times 6mm. I'm going to need this to be able to calculate stresses. So remembering that stress is equal to force over area, well, then I can calculate my stress. I'm going ahead and converting from kilonewtons to newtons because a really fun and amazing trick is that 1 Newton per millimeter squared is equal to 1 megapascal. This will save you a lot of pain and suffering if you remember that. Now we know the longitudinal strain, we know what the stress is, and those are connected by Hooke's law as long as we're inside of that elastic region. So now let's calculate our elasticity, which is simply going to be the stress divided by my strain. Since I had microstrains, I'm going to have to convert that to regular old average strains. You could just use the epsilon here if you wanted to, but if you want to write inch per inch or meter per meter, whatever it was, you can do that. Okay. And so with that, we get 100,182 megapascals, or 100.2 gigapascals, which makes a lot of sense. If you're worried on the fact that this is inch per inch here and everything else is metric, you don't need to be, because strains don't really have a unit. Inch per inch cancels. It's nothing. It's just to remind us that that was a strain. Yep. And that will be it. So, thanks for listening. If you want to have a little bit of extra work, you can try to calculate the shear modulus and see what that would be for this material. But that'll be all we do this time. And next time we'll work on some group problems. So, have a wonderful day. Bye-bye.